We've been talking about acids and bases, and last time we introduced the concept of pH, and we said that pH can be calculated by negative log of proton concentration. We said that pOH can be calculated by negative log of hydroxide concentration, and the sum of these two is 14. Now, if you have a strong acid, what do you know about the concentration of a strong acid, such as hydrochloric acid, and the concentration of proton? They're equal. How come?
Because a strong acid ionizes.
Exactly. A strong acid ionizes completely. This is a monoprotic strong acid, one ionizable proton, mono meaning one. And so hydrochloric acid ionizes completely to hydrogen ion and chloride ion, and these two concentrations are equal. So if I were to give you the concentration of hydrochloric acid, that would be equal to the concentration of proton, and you could get the pH by doing negative log of the proton concentration. Similarly, if I gave you a strong group 1 base, and remember, all group 1 containing hydroxides are strong bases. For example, sodium hydroxide, that would ionize completely to sodium ion and hydroxide ion. So what could you say about the concentration of this strong base and hydroxide ion? They too are equal. So if I gave you the concentration of a strong group 1 hydroxide, that's equal to the concentration of hydroxide ion, you would use this formula first to get the pOH, and you could get the pH by doing 14 minus the pOH. And I believe that is where we left off. Each of the classes at a slightly different point, which is why I have filmed multiple classes to show you.
So both strong bases and strong acids ionize completely?
Yes. I believe our last problem last time was that one, cesium hydroxide, correct?
Yeah.
Okay. There are 3 strong group 2 hydroxides, and these also ionize completely. By definition, a strong acid or a strong base ionizes completely when dissolved in water. If you have a strong group 2 base, for example, such as calcium hydroxide, strontium hydroxide, or barium hydroxide, these also will ionize completely, but there's a little trick in here, and that is that calcium hydroxide will generate 2 hydroxide ions for every 1 calcium hydroxide, same as the case for these two. So in this case, you would need to do a little bit of stoichiometry to determine the concentration of hydroxide ion, because you have a 1 to 2 mole ratio. And that's the example I'm going to point out here. Now there is one strong acid that's diprotic, and that's sulfuric acid. I'm not going to give you that because I don't want to confuse everything, and that's really very tricky depending on whether it's dilute or concentrated, so I don't want to make that any more confusing. But with these strong group 2 bases, for every 1 mole of base, you get 2 moles of hydroxide ions. So these concentrations are not equal. This is twice as much as this. So for example, in your notes, it says calcium hydroxide concentration is 1.4 times 10 to the negative 3 molar. I'm asking you to calculate the pH of the solution, figure out if it's acidic or basic, and explain. So this is the concentration given. Here's the 1 to 2 mole ratio. So to find the concentration of hydroxide ion, in order to find the pOH, you've got to do this 1 to 2 mole ratio, so it's 2 times that concentration. Here's your concentration of hydroxide ion. pOH is negative log of it, so it's going to be 2 point something, 2.55, again with the sig figs. Don't forget, pOH and pH sig figs start after the decimal point. 2 sig figs to match the 2 sig figs you were given. pH is equal to 14 minus the pOH, and you get 11.45, a basic solution since the pH is greater than 7. In purple is a very similar problem I'd like to walk through with you so you can see exactly how to determine the pH of a strong group 2 hydroxide. The concentration of strontium hydroxide is given at 2.3 times 10 to the negative 2 molar. We want to know the pH. We want to know if the solution's acidic or basic, and why. Why is this concentration not equal to the hydroxide ion concentration?
Because it's a group 2 base, so there's twice as many hydroxide ions as there are strontium ions. So
There are twice as many hydroxide ions as there are moles of strontium hydroxide, also strontium ion, but the comparison you're making is between the base and the hydroxide ion. So the first thing you're going to do is the stoichiometry, 2.3 times 10 to the negative 2 molar for strontium hydroxide. For every 1 mole of strontium hydroxide, you have 2 moles of hydroxide ion. So that's going to be 4.6 times 10 to the negative 2 molar hydroxide ion.
because you have to find out what the hydroxide.
Right, because that's the only way you can get pOH and then pH. So when they give you hydroxide ion or they give you a strong base, always go after hydroxide ion first, pOH, then pH. If they give you an acid, you can go right after the pH, provided that that acid is strong. If it's weak, it's a little bit different, a little complicated at this level. I will gladly show you at the end of the chapter for those of you who are interested, and it does link very much back to KEQ. All right. Once you know that, pOH is equal to the negative log of 4.6 times 10 to the negative 2 molar. It's going to be 1 point something. So you have negative log of 4.6 EE negative 2. 2 sig figs, 2 digits after the decimal point for pH or pOH. So pOH is 1.34. pH is 14 minus that. Maintain those 2 decimal places. The pH is 12.66. And why would this substance be basic? Basic solution because the pH is greater than 7. And why would this solution be more basic than a solution with a pH of 9?
Because it's more towards 14, which is the most basic.
More towards 14, or you can say the pH is greater, the pH of 12.66 is greater than the pH of 9. The higher the pH, the more basic, or you can say the farther it is from neutral 7.
Would it be still right if you said it's basic because pOH is less than 7?
Yes, but it's a very backward way to do it, so just be careful. So these are your 3 strong group 2 bases, so watch out for those, okay? All right, so what we're going to do here is we're really going to link some of the concepts we've talked about previously. If you don't have a periodic table out at this point, you want to grab one, you're welcome to grab mine. Calculator as well. What's really nice about this acid-base chapter is that we are going to be linking back to stoichiometry as well as solutions. And this is excellent review for your semester exam, which is not that far away. Yours is June the 1st. So really stay on top of everything now. You were just tested on 2 chapters. You probably know those. The acid base you'll have a good feel for. But especially some of the chapters from the third 9 weeks, you'll need to go back and review. And you'll have semester exam review sheets to better prepare you as well as problems to solve. All right, the other thing we want to do here, and this is really going to be a mathy type of day, in problem 6 and 7, this is going to majorly link acid and base chemistry with solution chemistry. There's nothing in this problem you don't know how to do already. If you look at number 6, you're given the mass of nitric acid, and you'll learn how to name the acids next time. It's dissolved in a final volume of 751 mils. We want to calculate pH. We want to know if the solution's acidic or basic. What formula do we use to calculate the pH of a strong acid? pH is equal to negative log of the concentration of proton, correct. So we're given a strong acid's ionized completely, so whatever the concentration of nitric acid is the concentration of proton. We're given the mass and we're given the volume. If we wanted to find the molarity, which is a unit of concentration, molarity is equal to moles of solute over the total volume of solution in liters. Well, in this problem, we're given the mass of nitric acid at 0.371 grams. We're also given the volume of solution at 751 mils. We need to get the concentration of nitric acid. How are we going to do that?
Convert grams to moles.
Convert grams to moles. We have 1 mole of nitric acid is equal to the mass in grams off the periodic table. And that's 63.0119. So the concentration of the acid is going to be that many moles over what?
751 liters.
To go from mils to liters, you move the decimal 3 to the left. And that's the concentration of the acid. Why is that also equal to the concentration of proton? Because nitric acid is a strong monoprotic acid. It has one ionizable proton. It ionizes completely. These concentrations are the same. So how do you find the pH?
Negative log, so 0.84 times 10 to the negative 3.
And that's going to be 2 point something.
2.106.
And that is correct. You have 3 sig figs, so 3 digits after the decimal is 2.106. This, of course, is an acidic solution. Because pH is less than 7. Yeah. That's an equal sign going the other way. And again, because nitric acid is a strong acid, it ionizes completely. And for the quiz, I'll tell you it's a strong acid or a strong base.
We should give a hint as to what it should be.
Exactly. For the test, you need to know your H-strong acids, and they're in your notes.
So pH doesn't have a
No unit for pH. The unit for concentration typically is molarity. I mean, we also have molality and mole fraction, but we primarily use molarity. Oh, sorry. Okay. Question 7 is grossly similar. I'd like for you to try question 7 with your question 6 framework in front of you. So I'll put 7 on the screen. Please fill out the pass. How'd we do? Another minute, you need?
Is there gonna be like an OH one of these that might pop up?
Yeah, you could do that, and I have more of those in a few minutes. That's what I got. Mm-hmm.
Something that could pop up in like AP Chem or something would be like the SrOH2 and then converting that all the way down to the pH.
honestly, that
with the molarity and stuff.
for a lot of chapters this year, I've given you a big chunk of the content that you might see in AP Chem. So for example, thermo, pretty well prepared already. Kinetics, when you look at the college chem or AP Chem chapter, I've probably given you about 65% of that chapter. Equilibrium, maybe only about 60% because there's a big chunk of equilibrium we don't do at the honors level. But the acid-base chapter in AP Chem is at such a high level that in regard to what you're getting this year, it's really low. It's so much, that particular chapter is so much harder that no, it's just a whole nother level of impossible. But you'll be set, don't worry. So there are certain chapters this year. I always try and give you the foundation. Like one of the things I showed you in drawing compounds was that Ku group, and that popped up on a recent AP exam. So I feel like if you've seen it multiple times and over a longer period of time, you're that much stronger with it. But even with the drawing of compounds and the shapes, the AP curriculum is so more extensive that it's hard to draw certain comparisons. Like you'll see some stuff, like even like Le Chatelier's principle. One of the reasons why I didn't want to skip it this year is when you see it twice, the kids are so good at it in AP. Most of you are pretty good at it now, but when you get to AP, you've seen it twice and you've done another lab on it, which really helps. But this chapter, there's so much in acid-base chemistry. All right, are we good here? Yes, yes? All right, so now we know how to get pH, and you don't have to write this again. And we know how to get POH, and we can get each of those from concentration of either proton or hydroxide ion respectively. Well, now what we want to do is we want to go backward. If I give you proton concentration, can you go to pH? And keep in mind, if I give you the concentration of a strong monoprotic acid, you know how to get here, and then you could get to pH. I think I did this backward. So you know how to go from here to here to here, and now the question becomes, can you go this way? Same thing here. For example, a group 1 hydroxide, you know, is equal to hydroxide ion concentration. You know how to get to the POH, but the question is, from the POH, can you go this way? And it's really pretty straightforward. The only thing that I think some kids get confused with is what buttons to push on their calculator. What you're going to find is that if you want to know the concentration of proton, that is equal to what I learned as the anti-log. I don't think you use that terminology anymore. It's second log. So it's 10 to the negative pH. Or if you want to know hydroxide ion concentration, that's 10 to the negative POH. And I'll show you how to use your calculators. So instead of going this way, which we know how to do, now we're going to take it the other way. Can you go from pH to proton concentration, or can you go from POH to hydroxide ion concentration? And then could you go to strong acid concentration, or even to the mass of a substance? So we can just keep doing stoichiometry to determine the quantity that we want. And that's what you're going to see here. So proton concentration, as I said, is 10 to the negative pH. Hydroxide ion concentration is 10 to the negative POH. If you were to multiply those two quantities, you get a very special KEQ quantity known as KW, ionization constant of water. We're not going to use this year, so I wouldn't worry about it. Let's take a look at several examples that are provided to make sure that you understand how to use your calculator. I have several out and I'll walk you through them so that you don't make a calculation error. The first one says that the solution has a pH of 3.45. We want to calculate proton concentration, 10 to the negative. Depending on your calculator, I'll pop a few up here so that you can see. So I just hit second log negative 3.45 close equals. I want 2 sig figs, so 3.5 times 10 to the negative 4 molar for concentration. If you have the multi-view, you're going to hit second log negative 3.45, hit the side button to take it down, and you've got that. If you want scientific notation on this one, you can go to mode and drag normal to psi, hit enter, clear, enter, and you'll get scientific notation there. And you can get scientific notation off here too. Does anybody have the very simple TI-30? Right, so this one you put in all backward. On this one, what you're going to do, and this works equally as well, 3.45 plus minus button, second log, and you've got it there. And some of these have mode abilities, and so second 5 puts it in scientific notation, and second 4 flows it out. So just make sure you know how to use your calculator, because some of you appear to still be making calculation errors, and they do get very expensive. Andrew?
Would you rather have them in scientific notation?
It really doesn't matter to me as long as you have the correct number of sig figs. But if you have like 0.000000000, that's just a nightmare to grade. I got to sit there and slash zeros. So in that case, yes. Yep.
I just did one like from the classwork, and I got it, and I put it back in, and it was about like 0.3 off. Like when I put the molarity back, when I did negative log of the molarity that I got.
Yeah, it depends on where you cut off your sig figs, but there's a little wiggle room to still be correct, so don't sweat it. All right. Okay. And this one is showing the pOH. It says the solution has a pOH of 1.245. Calculate proton concentration. I'm going to walk through the easy way. If you want to know proton concentration and given the pOH, get the pH. How do I get pH from pOH? 14 minus the pOH, so 12.755. Proton concentration is 10 to the negative pH. And here's your answer here. Again, 3 sig figs after the decimal point for pH, 3 sig figs. Also watch your unit here, molarity, for a unit of concentration. Let's work through number 3 together to make sure you're golden here. On number 3, a solution has a pH of 3.54. We want to calculate the proton concentration. That's 10 to the negative pH. So that's 2 sig figs. Second log of negative 3.54 is 2.9 times 10 to the negative 4 molar. Now, if I asked you for the concentration of hydrochloric acid, why would that be the same? Because hydrochloric acid is a strong acid that ionizes completely. On number 4, it says that the pOH is equal to 5.47. We want to calculate the proton concentration. So what do we need to do before calculating proton concentration? Got to get the pH. How do we get the pH? 14 minus that is 8.53. Proton concentration is 10 to the negative 8.53. And sig figs here are a little tricky, so it's going to be 3.0 times 10 to the negative 9 molar as the concentration of proton.
How does sig figs work?
The sig figs for pH, again, it's only after the decimal point, whereas concentration, it's just typical. All right? So I'll let you try number 5. Number 5 says the solution has a pH of 12.40. And we want to calculate proton concentration. So this is pretty straightforward. And what'd you get?
4.0 times
10 to the negative 13? Yep. All right, in your notes, there's a do now problem, which is similar to what we did previously, except you have a base here, so not terribly difficult, just a little backward before you can get pH. Where I've drawn this line is as far as your quiz goes. I would like to walk through 6 and 7 with you. This is a little bit backward. I'm 99% sure that's not on your quiz, which I will double check, but it is on your test. I'm going to walk through 6 and 7 with you, and then I'll let you give that do now problem a try, as well as number 8. The naming of acids we will hit next time with neutralization. Let's take a look at number 6. You're going to see we're going to process this very backward of what we did previously. On number 6, it says what mass of nitric acid. So we're looking for the mass of a strong acid. Previously we were given the mass of the strong acid. Must be dissolved in a final volume. So the total volume is 756 mils. To generate a solution that has a pH equal to 1.987. And that's all the information that they give us. And this becomes a puzzle. And if you like puzzles, you'll be very good at these types of problems. I want to know the mass of the acid. I'm given a total volume. I'm given the pH.
Shouldn't you convert milliliters to liters?
You will need mils to liters. So absolutely, hit that right away or write it down in liters, whatever's easier for you. How are we going to do this?
First, I'm going to find the concentration of nitric acid.
All right, so from pH, we can get the concentration of proton, which is equal to the concentration of nitric acid. So let's start there. How do we get concentration of proton?
10 to the negative 1.97.
You got it. So we have second log of negative 1.987. And that's going to be 1.03 times 10 to the negative 2 molar. And why is that equal to the concentration of nitric acid?
It's a strong acid.
Strong acid ionizes completely, one ionizable proton. Okay, if I have 1.03 times 10 to the negative 2 molar, that's moles per liter. I ultimately want to get to the mass of nitric acid. So what am I going to do?
You need to cancel out the liters in the bottom of the denominator, you need to multiply it by the liters.
Okay. And that'll get me to moles, right?
And then to cancel out the moles and get grams, you need to multiply it
By what?
by the molar mass,
You got it.
which is,
I think we did that one at 63.0119, if I'm remembering correctly. All right, let's see how that comes out. So we went from pH to concentration. From concentration, we multiply by the volume to get moles, and then we multiply by the molar mass from the periodic table to get the mass. So we've essentially just done everything backward of the long problems we did previously. Not hard, but let your units drive your problems, and you'll be far more successful with it. 7's a little bit backward, but certainly you're capable of it. On 7, we want to know the mass of sodium hydroxide. The volume is 546 mils, so you told me earlier that you know it needs to be in liters. And the pH is 11.087. So what are we going to do with this problem? We want the mass of a base.
to 10 to the negative 11.087.
If we do that, we'll get proton content. You can go that way, but it's a little trickier.
Yeah, just do 14 minus 11.
So get the POH first, do 14 minus that. And that can lead you to hydroxide ion concentration, which would be 10 to the negative 2.913. And why is that equal to the concentration of sodium hydroxide? Strong base, group 1. Now, if you had a group 2, you'd have to do a little stoichiometry in there. Be careful. All right, so now you have the concentration of base. You have 1.22 times 10 to the negative 3 moles per liter of sodium hydroxide. You ultimately want to get to the mass. How are you going to get rid of liters? Multiply by the volume in liters. And then how are we going to get to grams?
Multiply by the molar.
Yep. That's right around 40. I got squished, sorry. Yep. So you can see the problems go forward, backward, sideways, and you just have to let your units drive your problems. I think you'll be very successful with it. I'll put the answers up to the other problems, and there are a few things we need to decide, or I may leave you with those problems to do, and we can check the answers next time. Might be a better way to go. So what you want to make sure you understand today is how to calculate proton concentration from pH, and that can lead to concentration of strong monoprotic acid. So you're traveling this way. You want to make sure you understand how to calculate hydroxide ion concentration from POH, and that can lead to the concentration of a strong base. Watch the group 2 strong bases, because that can be a little bit trickier. Make sure you can link solutions in here. If I ask you for the mass, you want to be able to work through it. If given the mass, you also want to be able to start in that regard. On your classwork, we still have quite a bit of time, and that's what we're going to discuss. On your classwork at this point, you can do through 21. So you should have done through 10 previously, and now you can successfully complete 11 through 21, and all the answers with work shown is on Edline. Questions in regard to anything we've discussed today? Next time we'll get into the naming of acids, which is very straightforward. You'll be very successful with that. And then after that, we'll get into titration.